Hello students, in this video we are going to continue the lecture on analysis of switch reluctance motor using ANSYS Maxwell software, and in this software we are going to use RMXprt tool. Okay, before going to continue the second part of this video lecture, we'll just revive the part which is covered in the part 1 of video lecture. In the part 1 we had discussed that what is meant by the switch reluctance motor. The switch reluctance motor is the motor which works on the principle of reluctance, that is, rotor try to attain the position according to the value of reluctance or magnitude of the reluctance, and motor rotates. And the constructionally difference is that in this case the only stator is having winding, whereas rotor is without the winding, and the magnet required in this motor is very less, and hence this is the motor which is the solution for reducing the use of rare earth magnet in case of construction of the motor. Also, in first part we had discussed that how to design the switch reluctance motor by using the ANSYS Maxwell RMXprt tool. In this case we had discussed how to design the 550 watt motor, and it is of 8x6 type of the motor, where 8x6 means 8 is the stator number of poles and 6 is the rotor number of poles. And how to design that 8x6 550 watt and DC motor by using the ANSYS Maxwell RMXprt tool. So just we'll revise that part, or we'll try to design the motor again in short. Here also we had discussed this is the window of the ANSYS Maxwell software, and I'm going to open any one project. For example, I will open the project which we had already designed. So I will try to open any one example. Suppose I will open the project. Then we had discussed this is project manager. Through the view option you can control the view of the motor. See, in case of the view option, when we select the project manager, on the left hand side you will get the details of the motor. Apart from that, these are the different options through which you can control the display of the software. Now actually we have designed the switch reluctance motor, but here for the revision purpose we'll again design the motor. What we have discussed during the design, what we have to do, we have to go through this insert RMXprt design, through which you can insert the new design and you can provide the inputs as per your requirement of design. Also we have discussed there are different options like file, through which you can open or close the file, or you can go through the open examples which are already present. Then through the edit there are different options for the editing. Then through view you can control the view of the application. Then in project you can convert this example into the Maxwell 2D design, Maxwell 3D design, etc. Then in case of the machine you can go through the different options like winding, wire, units. Then in case of the RMXprt, these are the different softwares in different options through which you can perform the different activities. Like through the validation check we had discussed during the last lecture how to validate your design data. Then in tool there are different options. Then you can add the libraries, you can use the library tools, project tools, run script, etc. Then in the window you can create the new window. Then there are different options related to the window. Then through the help you can go through the Maxwell PDF file, then file related to the different project which are already present or given as an example. Okay, now actually what we have to do, we have to try to design the motor similar to the first example. So what I will do, I will go through the insert RMXprt design. So when I will press on the insert RMXprt design, there are the different options, like you can do the design and analysis of the different motors, like adjust speed synchronous machine, brushless permanent magnet motor, then DC machine, generic rotating machine, line started permanent magnet synchronous motor, permanent magnet DC motor, single phase induction motor, switch reluctance motor, three phase induction motor, three phase non-silent synchronous machine, three phase synchronous machine, universal motor, etc. Then we had discussed that we had designed the switch reluctance motor. So I will insert the switch reluctance motor RMXprt design. Then when I will go through the design, then of course for the switch reluctance motor design you have to give the input for the machine design, circuit design, then in case of the stator design, winding design, then rotor design, shaft design, and then you have to do the analysis. So this part we had already covered, so we directly start with the machine design. Then I will press on the machine. These are the different parameters which I need to give as an input. So first part is frictional loss, and the meaning of the frictional loss is nothing but frictional loss measured at the reference speed. So that frictional loss we had considered the 8 watt. So I give the frictional loss input as 8 watt. Then windage loss we had considered the 4 watt. Then reference speed is nothing but reference speed at which the frictional and windage losses are measured. That reference speed we had considered 3500 rpm. Then control type of DC, of course there are different options like DC and triple C, that is direct control and current chopped control. We had selected the DC. Then circuit type in case of the circuit type there are options like full voltage, half voltage, coupled coil. We had selected the full voltage option and will apply this design. Okay, now next part is the design of the circuit. So when I will press on the circuit design, first one option is lead angle. The meaning of which is lead angle of the trigger in electrical degree. So we had considered that lead angle of trigger in electrical degree is 0. Then trigger pulse. The meaning of the trigger pulse is that trigger pulse width in electrical degree. That trigger pulse width we had considered 120 degree. Then transistor drop. The meaning of the transistor drop is nothing but transistor voltage of drop of one transistor, and that transistor drop we had considered the 0.5. I will give the input as 0.5. Then total diode voltage drop. So we have considered that diode voltage drop as 0.5 volt. Thus we have provided the input for the circuit design. I'm going to apply this design and I will press the OK button. Now I have to make the design of the stator. When I double click on the stator, there are the different parameters like outer diameter, inner diameter, length, stacking factor, steel type, number of poles, membranes, yoke thickness, etc., which I need to give as an input. So outer diameter of the design under consideration, we had considered the stator outer diameter equal to the 120 mm. So I will put the 120 mm. Then inner diameter which is meaning of which is inner diameter of the stator core. That inner diameter we had considered 75 mm. Then length, the meaning of length is nothing but length of the stator core, length of the stator core. So we had considered the length of stator core equal to 65 mm. So I will just give the input as 65 mm. Then stacking factor is 0.95 only, that is stacking factor of the stator core. Then steel type, here we can decide the material for formation of the steel type of the stator core, that is to design the stator core we use the steel. But uh, we have already discussed that the performance of the motor also depend on the material which we are going to construct that part. So in this case you are having the different options. When you press on the not assigned part, you will get the material library, and there are different properties like name, location, origin, type, relative permeability of selected material, bulk conductivity of selected material, magnetic coercivity, core loss, thermal conductivity, mass density, and specific heat of the selected material. So we had selected the steel 1010 as the material. So I will select that part, steel 1010 as an material. Then number of poles, since we are going to design the 8x6 motor, where it is stator number of poles. So here number of poles of the stator we will consider as 8. Then embrace value, that is pole embrace is 0.5, and yoke thickness. So for the selected design we had uh, consider the yoke design, yoke thickness. Actually we had considered that yoke thickness equal to the, just a minute, 9 mm. So I will give the input as 9 mm. Okay, and I'm going to apply this design. Okay, and I will press the OK. Once you provide the input data for the stator design, the geometry of the stator is available here. Okay, so uh, you can go through the design. There are total 8 number of poles are there, but if there is any irrelevant data, then it shows the error in this bottom part. Okay, or there will be the message regarding the error. Now I will give the input for the winding. In case of the winding, you can provide the input as insulation thickness and adjustment, parallel branches, turns per pole, then number of strands, wire wrap, and wire size. So first part is insulation thickness, the meaning of which is thickness of the insulation between the stator core and field winding. So that insulation thickness, I will go through the design data. Insulation thickness is 0.3 mm. So I will give the input as 0.3 mm. Then end length adjustment is 0 mm. Parallel branches, number of parallel branches are 1. Turns per pole. Turns per pole we had considered the 20. Then number of strands. Number of strands are 1. Then wire wrap. Wire wrap thickness is 0.08, and wire size. Wire size is, you can select or 0 for auto design. So wire size is 1.628 diameter. Gauge number and diameter. So I will go through the selected part, that is 1.628, that is 14 gauge, and OK. If you go through the options for the wire wrap, also 0 for auto pickup in the wire library. If you are not having the details of wire wrap, wire size, then number of strands, then if you keep it as 0, it will select the auto design value. Okay, and then I will apply this design and I will press the OK. Okay, so you will get you have provided the stator details and stator winding details. Now you need to design the rotor. See, if you go through the geometry, the rotor is not shown. That means you have to design the rotor. So these are the input. Now what are the input for the rotor design? Outer diameter, inner diameter, length, steel type, striking factor, number of poles, branch, and yoke thickness. That means almost the parts are similar to the stator. So outer diameter of the selected rotor design is nothing but it is equal to the actually outer diameter of the rotor is nearly equal to the input diameter of the stator, inner diameter of the stator. So inner diameter of the stator we had selected 75 mm. So I will consider it nearly equal to the 74 mm. Then inner diameter of the rotor is 30 mm. Length of the rotor is 65 mm. Then steel type material considered steel 10. So I will select the material from the library steel 1010. Then stacking factor 0.95. Number of poles, as we had already discussed, we are going to design 8x6 machine. That means number of poles are 6. And embrace value, the embrace value we had considered it is equal to the pole embrace for the rotor is 0.5, and yoke thickness of the rotor is 9 mm. And we'll apply this design. So rotor part is available. Now if we press on the machine, we will get the display of both stator and rotor. See, this is the stator part, this is the rotor part, and winding will be available on stator part only. Now in case of the shaft, you are having option of either check or uncheck the magnet shaft. Since there is a requirement of magnet shaft, I will check the value and I will press the OK. Okay. Now we had also discussed how to do the analysis. In case of the analysis, first of all you have to add the solution setup. So in case of the solution setup, you have to give the details of your project. Like setup 1 is the solution setup, operation type motor, because we had selected the motor type. Then load type is you are having the option of constant speed, constant power, constant torque, linear torque, fan load. So we'll select the option of constant power. Then in case of the rated output power, actually we had designed the motor of 550 watt. So I will give the input in as 550. Then rated voltage is 48 volt. Rated voltage is 48 volt. Rated speed, we had considered the rated speed of 3500 rpm. Operating temperature 75 degrees Celsius. That means the analysis data or result data will be according to the operation of the or performance of the motor at 75 degrees Celsius temperature. And we are also having the option of use default. Then press OK. So now all the inputs which are required for the design you have provided. Then we had discussed during the last lecture how to analyze or validate your design data. Then for that purpose, just press on the analysis and analyze all the design data. So the progress of the analysis will be shown here, and it is showing that the analysis is going on. Once the analysis will be completed, then we'll validate the design data. If the design data is validated correctly, then you can go for the result. But if the validated design data is not validated properly, then it will show the error in this bottom part. Right now there is no any error, so just we'll check the validation of the design data. This green color indicates that design data is validated. That means the required required data for the design by using the ANSYS Maxwell RMXprt2 is validated. That is, design settings are validated, machine design, analysis setup, optometrics, all the parts is validated. That means we are on the right path. Now I will obtain the output parameter. So in this case, actually, okay, first of all, we'll go through there are different options like rename. If you want to rename the project, then you can delete the project. Then properties, that is properties of your project will be displayed. See, till now part we had discussed during the last lecture. Actually, in this second part, we are mostly going to focus or discuss what will be the output of the analysis. That is, which information we can achieve by using the ANSYS Maxwell RMXprt design. So, as we right click on the setup, we have discussed the option of rename, delete properties. Then you can disable the setup, you can analyze the setup, then you can submit the job. You will get the create quick report. So if we press the create quick report, there are different options related to the current, flux, inductance, percentage, power, torque, voltage, etc. If I press on the current, see, and press the OK, in here you will get the result. In terms of the result, actually you will get the current data. So in case of the current, you will get the input DC current, then you will get the idea about maximum phase current, rated phase current, etc. So in case of the current, what is the input DC current? The input DC current is nearly equal to the 800 ampere. See, during the starting part it is maximum, then it goes on reducing, and then it remains stationary. Okay, in the graph you are having the options like marker, trace characteristic, then add note, add limit line, view, then accumulate, then edit, modify the report template, import export, then copy bitmap image. Through this copy bitmap image, you can directly copy this graph and you can paste in your report. Okay, now regarding the current, maximum phase current, see, this is the maximum phase current. So maximum phase current is up to this value. This is current for different phases. Then rated phase current. What is the rated phase current? That value you had selected. So this is the rated phase current, and this is the maximum phase current against each phase winding. So this data is required for the providing the protection also. Then another parameter which information which you will get through the quick report is flux. When I will press on the flux, here you will get the flux. That is, first one is the flux linkage. When electrical degree is 0 degree, 10 degree, 20 degree, 30, 40, 50, 60, 70, 80, how the flux will go change. This information you will get here, and in case of the flux one, you will get the flux linkage also. So suppose I will press on the flux linkage, I will get the flux linkages also. Then another information, actually this information will be on the in quick report, because most of the time you are interested in the current value, flux value, etc. Then this is the best option. Then another parameter which will get through the quick report is inductance. I press the inductance, you will get the inductance parameter here. See, these are the this is the inductance pattern for the flux, and air gap inductance is also available. Now another information which will get through the quick report is percentage. So what is the meaning of percentage? See, once you press on the percentage, you will get the efficiency. So this is the efficiency. So maximum efficiency is almost equal to the 83%, and this is the graph. Efficiency goes on increasing, then it becomes stationary at particular value, and with the speed, this efficiency goes on decreasing. Actually, because we have designed the motor up to the 3500 rated speed, so up to that rated speed maximum efficiency is 83%, but if you go beyond the rated speed, then efficiency goes on decreasing. Then another parameter, so which information will get through the quick report is nothing but power. So if you go through the graph of the power, see, output power goes on increasing up to the rated speed, it is maximum, sorry, below the rated speed it is maximum, and then it goes on decreasing. Then next parameter through which you will get the information through the quick report is nothing but torque. See, the torque is this is the output torque, and this is the rated speed. Torque is maximum at the lower speed, and it goes on increasing, decreasing with increased speed. At rated speed, the torque requirement is as per the design value, and if you go beyond the rated speed, then torque goes on decreasing. The next parameter is voltage. Okay, once I will press on the voltage, the in the result sheet voltage is available. See, through the voltage sheet, if I will press on the phase voltage, I will get the graph for the phase voltage. See, this is the phase voltage graph, and graph is between phase voltage and in electrical degree. Okay, so this information we will get under the quick result option. Now another information which you will get is nothing but performance of the entire performance of the motor. So when I will press on the performance, there are different options. First one is the performance related to the FEA input data. So in case of the FEA input data, you will get information that what are the ampere parallel branches. 1, equivalent model depth is 65 mm, equivalent stator stacking factor is 0.95, equivalent rotor stacking factor is 0.95, region depth is 88.06 to 8 mm, and unit fractions are 2. Another information which we will get under the performance is full load operation of the motor. See, whenever you are actually going to check the performance of the motor and you have to test the motor in laboratory, you have to do the multiple setup or the hardware model, and you have to check the performance, and it because it requires the time. But through this software, it becomes easy. You will get the full load operation data easily, and in case of the full load operation data, which information you will get? What is the input DC current? 30,556.9 milliampere, that is up to the 13 ampere. Then what is the phase RMS current? up to the 14.996 ampere. This is the RMS current through the winding. Then phase current density is 72,04,800 ampere per square meter. Frictional and windage losses are 15,014.1 milliwatt. Iron core loss is 2.52 milliwatt. Windage copper losses are 66.06 watt. Transistor losses are 14.160 watt. Diode losses are 7.383 watt. Total loss is 102.637 watt. Then output power is 548 watt. Input power is 650 watt. Efficiency is 84.227 Rated speed is in Newton meter, that rated speed is 3985.24 rpm. Rated torque is 1.313 Newton meter. Flux linkage is 0.037 Weber. Stator pole flux density is 1.03286 Tesla. Stator yoke flux density is 0.8395 Tesla. Then winding resistance is 0.0734418 ohm. Winding leakage inductance is 37070 nanohenry. Iron core loss resistance 2176640 ohm. Frequency of phase current is 3.985 into 10 raised to minus 7 gigahertz. Maximum output power is 20,30,400 milliwatt. So this is the data we'll get under the option of full load operation. Then you can go through the material consumption. This is also main important parameter which is needed to decide the cost of the motor. So of course the motor consumption should be less, but for this motor you will get the idea about the motor consumption. So what is the data? Stator copper density is 8,900 kg per meter cube. Then stator core steel density is 7872 kg per meter cube. Rotor core steel density is 7872 kg per meter cube. Stator copper loss is 1.04415 kg. Sorry, stator copper weight. This is the kg, and we had selected the material is steel 1010. Stator core steel weight is 2.29736 kg. Rotor core steel weight is 1.27536 kg. Total net weight is 4.61687 kg of the motor. Then stator core steel consumption is 4.92722 kg. Rotor core steel consumption is 2.10761 kg. So this is the information related to the material consumption. Then you will get the information about the no load operation. So in case of the no load operation, what is the no load speed? 12,053 rpm. See, in case of the switch reluctance motor, the no load speed is higher. Then no load DC current is 4,346.07, that is 4.346 ampere. See, the full load operation current is maximum as compared to the no load DC current. So full load operation current we have discussed, it is up to the 13 ampere, and no load DC current is up to the 4 ampere. Then no load input power is 208.611 watt. Then start operation, estimated start torque is 53.6086. Estimated start DC current is 801.448 ampere. Maximum start current is 646.771 ampere. And last option through the performance is stator winding. So in case of the stator winding, number of turns per pole are 20, number of strands are 1, wire diameter is 1.628 mm, wire wrap is 0.08 mm, and coil half turn length is 88.0628 mm. So this is the information which you will get under the performance option. Now we'll go through the design sheet. So in case of the design sheet, this is the detailed design of your motor, which is the beauty of this software. This information you will get directly as an report. So what is the information in this detailed design sheet? Whenever mostly the manufacturers are going to manufacture the motor, at that time they will go through the, or they use through the this detailed design sheet. So what is the detailed design sheet? Detailed design sheet is divided into different parts like general data, then stator core data, stator coil data, rotor core data, material consumption, then full load operation data, node operation data, then start operation data, transient FE input data. So first of all, what is the general data of this motor? Rated output power of the motor is 0.55 kilowatt, that is 550 watt. Rated voltage is 48 volt. Given rated speed is 3500 rpm. Frictional loss is of 8 watt. Windage loss 4 watt. Type of the load is constant power operation. Type of the circuit is full load, full voltage. Lead angle of the trigger in electrical degree is 0. Trigger pulse width in electrical degree is 120. Total transistor voltage drop is 0.5 volt. Total diode voltage drop is 0.5 volt. And operating temperature is 75 degrees Celsius. Now we'll go through the stator core data. So what is the information available through the stator core data? Related to the stator core data, number of stator poles of the stator are 8. Outer diameter of the stator core is 120 mm. Inner diameter of the stator is 75 mm. Yoke thickness is 9 mm. Pole impedance is 0.5. Length of the stator core is 65 mm. Stacking factor of the stator core is 0.95, and type of the steel is steel 1010. Then stator coil data, slot insulation thickness is 0.3 mm. End length adjustment is 0 mm. Number of parallel branches in case of the stator coil are 1. Number of turns per pole are 20. Number of wires per conductor is 1. Wire diameter mm is 1.628 mm. Wire wrap thickness is 0.08 mm. Then slot fill factor is 45.7813. Then rotor core data, number of rotor poles are 6. Length of air gap mm is 0.5 mm. Inner diameter of the rotor is 30 mm. Yoke thickness is 9 mm. Pole impedance is 0.5. Length of the rotor core is 65 mm. Stacking factor of the rotor core is 0.95. Type of the steel, material is steel 1010, and magnetic shaft is, that is magnetic shaft is available. In case of the material consumption, stator copper density is 8900 kg meter cube. Rotor core steel density is 7870 kg per meter cube. Then rotor core steel density is 7872 kg per meter cube. Then stator copper weight is 1.04415. Steel core steel weight is 2.29736. Rotor core steel weight is 1.27536. Total net weight is 4.616 kg. Then regarding the full load operation of the data of the motor, input DC current is 13.55 ampere. Phase RMS current is 14.99 ampere. Phase current density is 7.20 ampere per mm square. Then diode loss is 7.387 3 38 watt. Transistor drop is 16.16 watt. Total loss is 102.63 watt. Output power is 548.095 watt. Input power is 650.73. Efficiency is 84.2274. Rated speed is 3985 rpm. Rated torque is 1.31 Newton meter. Flux linkage Weber is 0.037. Stator pole flux density is 1.03 Tesla. Stator yoke flux density is 0.83 Tesla. Rotor pole flux density is 0.78 Tesla. Rotor yoke flux density is 0.31 Tesla. Coil length per turn are 176.126 mm. Winding resistance in phase is 0.0734 ohm. Winding resistance at 20 degrees Celsius ohm is 0.064 ohm. Winding leakage inductance is 0.037 millihenry. Iron core loss resistance is 2.17 into 10 raised to 6 ohm. Frequency of the phase current is 398.524 Hz. Maximum output power is 2033.4 watt. No load operation data. In case of the no load operation data, no load speed is 12053.1 rpm. No load DC current is 4.346 ampere. No load input power is 208.611 watt. In case of the stator operation data, estimated start torque is 53.6086 torque Newton meter. Estimated start DC current is 801.448 ampere. Maximum start current is 646.771 ampere. Then in case of the transient API input data, for armature winding, number of turns are 40, parallel branches is 1, terminal resistance is 0.0737 ohm, end leakage inductance is 1.18958 into 10 raised to minus 5, 2D equivalent value, equivalent model depth is 65 mm, equivalent stator stacking factor is 0.955, equivalent rotor stacking factor is 0.95, and estimated rotor inertia moment, that is 0.0014 kg per meter square. Okay, this is the detailed design sheet. Now another beauty of this software is that you will get the curves, that is graph, also easily. So if you press on the curves, but there are different curves are available. So we'll go through the one by one parameter. First one is the flux linkage versus current at various position. That means related to the movement of the rotor. That is when rotor is at 0 electrical degree, 20 electrical degree, 30, 40, 50, 60, 70 and 80 electrical degree respectively, and you are having the different graphs. Okay, if we press on this graph, there are marker option, that is suppose add X marker, add Y marker, then export marker table, export delta marker table. Then if you want to add the node, then in case of the view option, there are, you can zoom in, zoom out the graph. Then in case of the edit, you can copy the setting, you can reset the setting, then copy bitmap image, that means this image will be directly copied, and when you press in word file, paste in word file, will get, you can import this data easily. Then second graph option available is input DC current versus speed. See, whenever the speed is less, at that time current is maximum. Whenever speed goes on increasing, input DC current also goes on decreasing. Third one, efficiency versus speed. Of course, we have seen through the detailed design sheet, maximum efficiency is up to the 84.3%. But this efficiency is zero at the initial speed, and when speed goes on increasing, efficiency goes on increasing, and it is maximum at the rated speed. But when we go beyond the speed, then efficiency again goes on decreasing. Then output power versus speed. Here output power in watt and speed is in rpm. This output power also goes on increasing. It is maximum at the rated speed and then again goes on decreasing. Then output torque versus speed. Output torque is maximum at less speed, and whenever speed goes on increasing, torque goes on decreasing, and then it becomes stationary at particular value. But beyond the rated speed, this torque again goes on decreasing. Next parameter is maximum phase current. So this is the phase current in ampere, and it is with respect to the electrical degree. That is, here the graph is at electrical degree of with span of gap of 125 degree. That is at 0, 125, 250, 375, 500, 675, and 750. So this is the graph for maximum phase current, and from this information you will get the idea about maximum current. That is, it is up to the 620 ampere. Then next graph is straight to the rated phase current. So this is the graph of rated phase current with respect to the rotor position or electrical degree. So this phase current also goes on increasing, then becomes decreasing, then at unaligned position it becomes 0, then goes on increasing, then goes on decreasing. So this is the graph of rated phase current with respect to the electrical degree. Then flux linkage. So this is the graph of flux linkage in Weber with respect to the electrical degree. Of course, this flux linkages goes on changing with respect to the rotor position. So this is the triangular waveform for the flux linkage. The next graph is air gap inductance. So of course, air gap inductance is also changes as per the unaligned or aligned position of the rotor. So this is the graph which shows the variation of the air gap inductance with respect to the electrical degree. Then next parameter is phase voltage. Actually, this is the graph of phase voltage. See, the square graph is available for the phase voltage with respect to the electrical degree. So this information you will get easily through the performance option. Now again we will go through the setup, and there is another parameter is related to the design sheet. So that part, this design sheet we had already discussed. That is information related to the general data, stator core data, stator coil data, rotor core data, material consumption, then no load operation of the data, start operation of the data, transient AP input data, etc. Then curves also we had seen. Then through the export you can export this model, that is simpler model. You can export as motor CAD project, you can custom design sheet, you can put as simpler model, and you can give the path. Suppose I will give the desktop and I will press the open. So through this it will export the, it will take time, but it will explore the simpler model also. Then create Maxwell design and create ANSYS design. In case of the create ANSYS design, you can directly import the ANSYS design. But another beauty of this software is that you can directly convert this RMXprt design model into the Maxwell 2D design. So that Maxwell 2D design or Maxwell 3D design can again use for the further analysis. So just for this project, we'll try to convert this design into the Maxwell 2D design. But before going to Maxwell 2D design, we'll discuss the part that through the RMXprt design, we can design the different type of the motor. In this case, we have discussed about the design of the switch reluctance motor. Then how to analyze the data, that part we had discussed. Then also we had discussed how to provide the input. Then how to validate the design data, how to import the report, that part we had already discussed. Now I will just convert this setup into the Maxwell 2D design. So create Maxwell design. There are different options. Either you can directly convert this model into the Maxwell 2D design or Maxwell 3D design. Here I will convert it into the Maxwell 2D design and I will press the OK option. It will take some time to convert this design into the 2D design. See, actually this is the part which is shown here. It is related to the converter and supply part related to the each phase winding. That is, see here, total 48 volt is divided into the 24 volt, and this is the converter part which is providing the supply to the each phase of the winding. This is the total entire portion which provide the supply. Yes, now this is the Maxwell 2D design for the given input. Similarly, you can convert this design into the Maxwell 3D design. So see here, if you go through the project manager, actually we had designed this motor RMXprt design 5 for switch reluctance motor. For Maxwell 2D design is available. So there are different component like 3D component, model, boundaries, excitation, parameters, mesh, analysis. Here again the procedure how to analyze the 2D model. That is, you have to give the select the boundaries, you have to provide the excitation, and through the further analysis you can check the performance of this 2D model also. Okay, so in this video lecture we had discussed, that is, first of all we had done the discussion about the switch reluctance motor. Then we had just revised the part which is covered in the part 1, how to provide the input data and how to validate the design data. Then we had discussed about how to do the analysis and how to validate the design, and discussion about the result output data which is available from the insert RMXprt design tool. And then in last part we had discussed how to convert the RMXprt design into the Maxwell 2D design. Of course, those students who are having the interest, they can make the more practice and uh, get the become the expert in this Maxwell software. And the use of this or this skill will be helpful for the student to uh, get the job in the design part of the motor, or those students who are having the interest in the design or simulation, they can make the more practice on this one of the software, that is ANSYS Maxwell software for the analysis purpose. Okay, thank you.